Hey, good evening, guys. Welcome back to another episode of Algorithm Challenge. Um, I'm happy to announce that today is the 40th day since I started my challenge. It's been a while. It's been a quite a ride, um, but we still managed to complete almost all the algorithms, just the theory-wise, of course. But yeah, so I think. From almost zero to that level in 40 days, it's quite a feat. So thank you guys all for watching also and um and leaving comments to motivate me and subscribing. That helped me a lot. Anyways, today we're gonna move on with the dynamic programming. And I told you guys yesterday that I'm gonna explore a problem. We're gonna try to solve a problem that uses the general template of the dynamic programming, the top-down approach. And then later, we're going to also see how we can implement it in a bottom-up way. So I'm going to share my screen with you guys. 1 second. And it seems like it's lagging again. Yep. Yes, guys, we're back. Sorry. Another technical issue. I think if you've been watching my videos, you guys must know that it's like an everyday occasion by now. I'll share my screen again. Voila, it's working. Okay, we're looking at Leetcode 746, min cost climbing stairs. So given an integer array cost where cost I is cost of ith step on a staircase, once you pay the cost, you can either climb 1 or 2 steps. And we have to return the minimum cost to reach the top of the floor. If you see the test case 1, um, the cost is 10, 15, and 20. And we start at either index 1 or index 0. So you start from either 10 or 15, and we have to reach the top of the floor, which is index 1, 0, 1, 2, 3, right? It's not inside the list, but once you reach index 3, you already know that you're on the top of the floor. So the the minimum, of course, in this case, the minimum cost to reach the top of the floor is by starting at index 1, which is 15. It's because from 15 you can jump 2 steps, right? Because you said they explicitly said we can either climb 1 or 2 steps. So from the first index we can climb 1, 2, and then get out of the bounds. Let's see the test case 2. There's a series of numbers, and the output is 6. You start as index 0, and then the top priority here is, of course, as you can see, 100, evading 100. So you jump, you do 2 steps, and then from here you do 2 steps again. From here you do 2 steps again, and here, because if you do 2 steps, you're gonna meet 100. So you do 1 step, and then meet 2 steps again, 1, and then voila, that becomes 6. From index 9, you pay 1 and then climb 1 step to reach the top. I think by now you guys understood what this question is about. Uh, as always, the question is not that hard. Understanding question is not that hard. I think the harder part is trying to visualize it using using the code. You want to try to do things with your code and to solve this problem. And that's the hard part. At least for me, it is. So for dynamic programming, in order to solve the question, you need 3 things. The first of all, you need um, a function that will compute the answer. So what is a function that will compute the answer in this case? Here, we know that cost I is cost of ith step on a staircase, right? So let's say that we define a function called dp. So dp, and then what will be its argument? It will be I, right? Because I is the ith step. And if you do dpi, that means it's the minimum cost of the ith step. So the value of this function is our answer, basically. And this I here, the number of steps, is the state variable. And that is also the important thing that we have to let ourselves know when we're trying to solve the dynamic programming question. I said yesterday that most of the case it's indexed along the array, but it can also be other things as well. So it's important to specify this and specify the state variable and find out the function that will compute the answer. Now we also have to find the recurrence relation to transition between the states. What this means, recurrence relation is like what we did yesterday, a Fibonacci sequence. There's factorial of number, and there's merge sort. What's the similarity of these three sequences or functions? The similarity is that you are using the previous state to calculate the final answer. So you can see from here n-1, n-2, that's previous step, and a step before the previous step. You're all to find a factorial, you utilize the step before. In order to do a merge sort, you do the half of the amount, and that also counts as a previous step. And that kind of mathematical function, mathematical relation is what we need in order to either recursively implement a top-down approach or iteratively implement the bottom-up approach. So what is the recurrence relation in this case in order to calculate the min cost climbing stairs? So we know for starters that to reach step I, we can either come from I-1 or I-2, right? Because it said we can climb 1 or 2 steps. So let's say that you want to reach the 50th step, you can either come from 48 or 49. Now, so therefore the cost of each step, cost to reach the step I is the minimum cost to reach I-1 plus the cost of step I-1, or the cost to reach I-2 plus the cost of step I-2, right? I'll just write it down here. Cost to reach step I, minimum of the cost is the min of cost to reach I-1. This is just the general. I'm not writing the whole function here, just trying to show you guys how this works, plus the cost of the step itself, which is I-1, and or cost to reach I-2 plus the cost of step I-2. So whatever is smaller is the minimum cost to reach the step I, right? Because we are choosing from either climbing one step or climbing two steps, right? So this gives us the recursive relation that we can use in order to recursively calculate the minimum cost of reaching a, a certain step on a staircase, right? And that we're going to code it later. Finally, we have, okay, so now we have the function that will compute the answer, which is dpi, and we have defined a state variable. Also, we have the recurrence relation to transition between the states, uh, which is the minimum of cost to reach I minus one plus cost of step I minus one and cost to reach I minus two plus cost of step I minus two. Now we need a base case. So base case where the function will stop, right? So when would it stop? It will stop when the cost to reach first step is simply the cost of the first step. So it's when dp0 is equal to cost of 0, right? Just cost to reach first step is simply the cost of the first step. Or it's, one second. Okay, guys, it just, yeah, so we were defining the base case. So that's when the dp0 is equal to cost of reaching the first case, or it's when I is less than I is less than minus I is less than 1, right? Um, so in that case, it will return 0. Or also because since we're going to use the memoization um, to save the base case in a hash function, hash map. So in that case, we're also going to stop running the recursive function. So yeah, now we have function that will compute the answer, recurrence relation to transition between the states, and a base case. Now let's try to code it. So we have to start with the function, the dpi. That will be define dpi. Now the first condition was if I is less than 1. If I is less than 1, then it's a base case. It hits the base case, so it's returning 0. Or if I is in memo, so in memoization, then return the memo of I. The ith case in order to climb the stairs. Now we define the recurrence relation, and that will be, so memo I is like the relation that we're going to continue running unless it hits the base case. And what I previously showed you is the cost to reach the step I is the minimum of cost to reach I minus 1 plus cost of step I minus 1, and cost to reach I minus 2 and cost of step I minus 2. So whichever is smaller, we choose it at each state. So that would be minimum of dp I minus 1 plus the cost of I minus 1 and comma dp of I minus 2 plus the cost of I minus 2, right? And at the end, we have to return the ith state of the memoization so that it keeps on flowing. We shouldn't forget to initialize a hash map. So that would be an empty set in Python. And at the end, return the dp of length of the cost because um, that is the total cost to reach the top of the floor. So yeah, let's try this code and see if this works. I think there was some problem with indentation. Name I is not defined. Uh, let's see. dp I minus 1 plus I minus 1. Yeah, this has to work inside the dp function, so this has to go here. Let's see if it works again. List is not callable. No, the recursive function is not callable. I minus 2. Wait, guys, this has to be a state variable, so it has to be a cost of I minus 1. So we have to use the square brackets. See if this works now. Oh yeah, so now it works. We can see that for test case 2, output is 6 and it's as expected. Same goes for case 1. So that was till now, that was the approach using top down. And it is sometimes simpler to do this approach, although we can optimize a bit more than use a bottom-up approach, which is in most of the times um, uh, has a better time complexity. So how are we gonna convert it into bottom-up? I'll quickly write it down here. I don't think we have to run it again, but yeah. So we start by implementing the top-down approach, and we initialize an array that is sized according to the state variables. Um, and we also set the base case, same as the ones we are using in the top-down function. Yeah, I don't think I have to write it down. I'll just try to explain it in words. We set our base case, and we write a for loop. In this case, we iterate over our state variables. And if we have multiple state variables, we will need the nested for loops because in the top-down approach, the recursive call does that function, but in the for loop, it doesn't have that. So we would have to use the nested case. And for each iteration of the inner main loop, it represents a given state and is equivalent to a function call to um, the same state in top down. So yeah, uh, maybe tomorrow we're gonna try to use the bottom up approach instead of top down. That we can also see, I can also see what fits better for me, although it is better for interviews to know both approaches. Um, yeah. And we're gonna do the 1D state and then the multi-dimensional state for dynamic programming. So yeah, stay tuned and leave a comment if you guys have any questions. And see you guys tomorrow. 1 second.